You enabled Secure Boot. You're sure you did because you went into your BIOS, found the setting, switched it on, saved, and rebooted. And Windows 11 is still telling you your PC isn't supported, or you enabled it and your Linux installation stopped booting entirely, or you've been dual booting Windows and Linux for months and everything was fine until a recent update, and now one side or the other is broken. You're not alone. Thousands of users are running into exactly these scenarios in 2026, and the reason it's happening now, specifically, is not random. There's a very specific technical story behind why Secure Boot is causing this much trouble this year, and once you understand it, the fixes become a lot clearer. Let's start with what Secure Boot actually does, because confusion about the mechanism is responsible for a significant portion of the troubleshooting rabbit holes people fall into. Secure Boot is a feature built into the UEFI firmware on your motherboard. When your computer starts up, before any operating system loads, the firmware checks a cryptographic signature on your bootloader, the small program that starts your OS. If the signature matches a certificate stored in your firmware's trusted key database, the bootloader is allowed to run. If it doesn't match anything trusted, the firmware refuses to proceed, and you get a security error instead of a booting operating system. This mechanism exists specifically to stop bootkit malware, malicious software that tries to hijack your system at the lowest possible level before any antivirus or security software has a chance to run. Secure Boot is a real defense against a real category of attack, which is why Windows 11 requires it and why disabling it entirely while it fixes some problems isn't actually the answer. Now here's the specific thing that's making 2026 different from previous years, and why Secure Boot problems have spiked, even for people who haven't changed anything about their setup. Microsoft is in the middle of retiring the certificate that has underpinned Secure Boot compatibility for over a decade. The 2011 Microsoft UEFI Certificate Authority, the cryptographic key that nearly every PC on Earth trusted by default for signing bootloaders, is being replaced by a newer 2023 UEFI Certificate Authority. New bootloader components going forward are being signed with the new key. If your firmware's trusted certificate database doesn't include the new key yet, bootloaders signed only with the new key won't be trusted. If it doesn't include the old key anymore, bootloaders signed only with the old key won't be trusted either. And if you're running Linux alongside Windows, the software that Linux uses to boot under sec your boot, a program called shim, needs to be correctly signed for whatever certificate state your firmware is in. This is the technical ground zero for a large portion of the Secure Boot problems people are hitting right now. With that context established, let's go through the actual problems and their actual fixes, one by one. The first and most common scenario: you enabled Secure Boot in your BIOS, but Windows 11's PC health check or setup is still saying your PC doesn't meet requirements. Before anything else, confirm that Secure Boot actually enabled correctly. BIOS settings don't always take effect the way you'd expect. Some firmware requires you to save and exit, fully power off the machine, not just restart, and then power back on before the change registers correctly. Do a full power cycle, not just a reboot. Then boot into Windows, press the Windows key plus R, type msinfo32 and press enter. In the system information window that opens, find Secure Boot State in the right pane. It should say on. If it says off or unsupported, the setting either didn't save or something else is preventing it from activating. If Secure Boot shows as unsupported in msinfo32, the most common cause is that your drive is still using the older MBR partition scheme instead of the newer GPT scheme that Secure Boot requires. You can check this by pressing Windows key plus X, selecting Disk Management, right-clicking your system drive, selecting Properties, going to the Volumes tab, and reading the partition style line. If it says Master Boot Record, MBR, that's your problem. Converting an MBR drive to GPT without losing data is possible using Windows' built-in MBR2GPT tool, but it requires the process to be done correctly, and it's worth making a full backup before attempting it. Run the command mbr2gpt-validate.disk.0 in an elevated command prompt. First to confirm your drive qualifies for conversion, then mbr2gpt, convert disk.0 to. Perform it. After the conversion, re-enable Secure Boot in your BIOS, and Windows should now recognize the configuration correctly. If your drive is already GPT, but Secure Boot still shows as unsupported, the issue might be that your BIOS is in legacy or CSM mode rather than UEFI mode. CSM, the compatibility support module, is a setting that makes modern UEFI firmware behave more like old BIOS for compatibility with older operating systems and software. When CSM is enabled, Secure Boot typically cannot function. Go into your BIOS settings, find the CSM or legacy boot option, and disable it. Then re-enable Secure Boot and check again. The second scenario: Secure Boot is on and working for Windows, but your Linux installation stopped booting after you enabled it or after a recent update. This is the scenario most directly connected to the 2023 certificate transition described earlier. When secure boot is enabled, Linux can't boot directly. It needs to go through a signed bootloader. Most major Linux distributions use a program called shim for this. Shim is signed by Microsoft's certificate, which firmware trusts by default, and shim then verifies and launches grub, which then loads the Linux kernel. If any part of this chain has a signature that your firmware doesn't trust, the boot fails. The first thing to check in this scenario is whether your distribution's shim is current. Open a terminal in Linux, if you can still access it by temporarily disabling secure boot, and check your shim package version. On Ubuntu and Debian-based systems, run dpkg-l grep shim. On Fedora and R shell-based systems, run rpm cuqa grep shim. Compare what you see against your distribution's current release. If your shim package is old, particularly if it predates mid-2025, it may be signed only with the old 2011 certificate, while your firmware, if recently updated, may now only accept the newer 2023 certificate, or vice versa. The fix is updating the shim package and the signed bootloader. On Ubuntu, Debian, sudo apt update and sudo apt install. Only upgrade shim signed grub EFI CMD64 signed. On Fedora, rel, sudo dnf update shim x64, grub2 EFI x64. If you can't boot into Linux at all because secure boot is blocking it, you have two paths. The easier path is temporarily disabling secure boot in your BIOS, booting into Linux, running the shim update, then re-enabling secure boot and testing again. The more controlled path is booting from a Linux live USB, mounting your installed system, and running the update from the live environment without touching your secure boot settings. The live USB path is preferable because it doesn't require you to disable secure boot even temporarily, and it confirms that you have a working recovery environment on hand, which you should have anyway for situations exactly like this one. The third scenario, both Windows and Linux were working fine in a dual boot setup, and then a Windows update or a Linux update broke the Linux boot entry. This is a recurring source of pain for dual booters, and it has a specific cause. Windows updates, particularly major ones, sometimes rewrite the bootloader configuration or modify the EFI partition in ways that remove or overwrite the grub boot entry that Linux uses. The symptom is that after a Windows update, rebooting brings you directly to Windows, without ever showing the boot menu where you'd normally choose Linux. Linux is still there on the drive. It hasn't been deleted, but the pointer to it in the firmware's boot order has been overwritten. The fix for this is to reinstall grub from a Linux live USB. Boot from your live USB, open a terminal, and mount your Linux installation. You'll need to mount the root partition and the EFI partition. The exact device names depend on how your drive is partitioned, but typically, sudo mount /dev sda2 mnt, replacing sda2 with your actual Linux root partition, then sudo mount .dev sd1 mnt boot.efi, replacing SDA1 with your EFI partition, which is usually the first partition on the drive, and formatted as FAT32. Then bind mount the necessary system directories, sudo mount, bind, dev, /dev, sudo mount, bind proc, emit proc, sudo mount, bind sys, emit sys, then crut into the mounted system. Sudo crut.jmnt, inside the crut, run, grub install, target Circus 664 EFI, EFI directory, boot, EFI, bootloader ID Ubuntu. Replace Ubuntu with whatever your distribution is called. Then run, update grub, exit the crut with exit, unmount everything, and reboot. Your dual boot menu should reappear. If you want to prevent Windows from overwriting the grub entry in the future, there's a partial mitigation. In your BIOS boot order settings, move the grub.linux EFI entry above the Windows Boot Manager entry. This doesn't prevent Windows from creating its own boot entries, but it means your firmware defaults to grub first, which can then present both Windows and Linux as options, rather than Windows Boot Manager loading Windows directly without showing any menu. The fourth scenario, you're getting a secure boot violation error specifically when trying to install a new Linux distribution, or the installer. Boot's fine from USB, but the installed system won't boot afterward. This is the most direct manifestation of the 2023 certificate transition. If your distribution's current installer uses a shim signed only with the new 2023 certificate, but your firmware's certificate database hasn't been updated to include the new certificate yet, the installer will be blocked before it even starts. If the installer is signed with a certificate combination, Your firmware accepts, but the installed shim on the target system isn't properly configured for your firmware's trust state. You get a system that boots from the USB but fails to boot once installed. The first fix attempt here is updating your firmware. Use the FWPD tool, run sudo fwupdmgr get updates to see if a firmware update is available for your machine. If one is available, check your manufacturer's support site for your specific model number before applying it. Some HP and Fujitsu models have known issues with standalone secure boot certificate database updates that require a full firmware update from the manufacturer, rather than a direct database update. If a firmware update is available and there are no known issues for your model, apply it. Sudo fupdmgr update. After the update, reboot and try the installation again. If no firmware update is available, particularly on older hardware whose manufacturer has stopped providing updates, you have a few options. One is checking whether your distribution offers an older installer image that uses a dual-signed shim compatible with both the old and new Fedora, and RHEL have released dual-signed shim packages specifically for this transition period. Downloading a recent installer image from these distributions' official sites gives you the best chance of getting a shim that works with your firmware's current state. A smaller or less actively maintained distribution may not have updated its installer yet, which is a signal to either wait for an update or switch to a distribution that has addressed this. Another option, specifically for hardware that will never receive a firmware update, is manually enrolling the new certificate into your firmware's secure boot database using the mokutil tool. This is more advanced, but entirely possible. Run sudo mokutil, import path to what certificate.ror on a working Linux system, reboot, and follow the prompts that appear on the blue MOK management screen before the OS loads. You'll be asked to confirm the enrollment of the new certificate, and once enrolled, bootloaders signed with that certificate will be trusted. The certificate you need is the new Microsoft UEFI CA 2023, which can be downloaded from Microsoft's official documentation on the Secure Boot Certificate Update. The fifth scenario, you're on a clean dual boot system that's working, but you're worried about what happens next when you run updates. This is the right question to be asking proactively, and the answer is straightforward. Before running any major update to your bootloader, shim, or kernel, particularly on the Linux side, take two steps. First, create or verify you have a bootable live USB for your Linux distribution. If something goes wrong with the boot chain, this is your recovery tool and it costs nothing to have ready. Second, make sure your firmware is current using fwupdmgr before running the update. A firmware that has the 2023 certificate enrolled is in a much more stable position for the coming months than one that hasn't been updated. After the firmware update and after the shim update, reboot and confirm both Windows and Linux boot normally before calling it done. One thing worth understanding about the secure boot requirement check in Windows 11 specifically. Enabling secure boot is necessary but not always sufficient for Windows 11 compatibility. The PC Health Check tool and the Windows 11 Setup Screen Check for Secure Boot, TPM 2.0, a compatible CPU, and minimum RAM and storage simultaneously. If you've confirmed Secure Boot is on and the check is still failing, use MSINFO32 to verify your TPM status as well. Look for TPM version and confirm it shows 2.0. If it shows 1.2 or not present, check your BIOS for PTT on Intel systems or FTPM on AMD systems and enable it, then recheck. Many systems that appear incompatible with Windows 11 turn out to be fully compatible once both Secure Boot and TPM are enabled. They were simply shipping with both features disabled by default, invisible to users who had no reason to explore those settings. For anyone reading this who manages multiple machines, a small office, a school lab, a personal collection of computers, the most efficient approach to this entire transition is running an inventory pass before you need to fix anything. Check secure boot status with mokutil, SB state on each Linux machine. Check firmware update availability with fwupdmgr, get updates on each machine. Update firmware where available, update. Shim and bootloader packages on each Linux installation, and document which machines have the new certificate enrolled and which don't. This costs a few hours now and saves a significant amount of reactive troubleshooting later, because the machines that aren't updated will eventually surface a secure boot problem when the next major system update touches the boot chain, and you'd rather be in front of that than behind it. The final point worth making clearly, disabling secure boot entirely is not the recommended solution for any of the problems described here, even though it does make them go away in the short term. Secure boot provides real protection against a real category of threat. Bootkit malware that specifically targets the pre-OS environment, because that's where conventional security software can't see it. Disabling secure boot to avoid. The complexity of the certificate transition means trading a difficult configuration problem for a permanent security reduction. The fixes described in this article keep Secure Boot active while resolving the underlying certificate and configuration issues. They take more work than flipping a single toggle, but they leave you with a system that's both functional and secure, which is the outcome that's actually worth spending an afternoon on. There's a sixth scenario that doesn't get enough attention in most secure boot troubleshooting guides. The BIOS resets secure boot settings after a power loss or CMOS battery failure, and suddenly a system that was working is broken again. Older machines, particularly desktops and laptops that are several years old, sometimes have CMOS batteries that are weakening or dead. When the CMOS battery can't hold the charge, the motherboard loses its stored settings every time the machine is fully powered off. And that includes your secure boot configuration. If you're finding that secure boot keeps reverting to disabled even though you keep re-enabling it, or that your secure boot mode keeps flipping back from custom to setup mode, a failing CMOS battery is a likely culprit. The fix is a new CMOS battery. It's a CR232 coin cell on most desktop and laptop motherboards, costs less than a few dollars, and replacing it is typically a straightforward process on desktop systems. On laptops, it's often accessible under the bottom panel. Once replaced, re-enter your BIOS, re-enable Secure Boot, save, and the settings should persist through power cycles. A seventh scenario that trips up users, specifically on machines that have had their operating systems reinstalled or reconfigured, is secure boot mode confusion. Your BIOS may show Secure Boot as enabled, but the mode listed may be setup mode or audit mode, rather than user mode. In setup mode, the firmware doesn't actually enforce the Secure Boot restrictions. It's in a state meant for enrolling new keys and certificates, not for protecting the boot process. If your system is in setup mode, bootloaders will load regardless of whether they're signed, which means Secure Boot isn't actually doing anything despite appearing to be enabled. The symptom is that Secure Boot shows as on in the BIOS, but Windows 11 or SINFO32 still reports it as not enabled or not supported. The fix is to exit setup mode. In most BIOS interfaces, this is called Restore Factory Keys or Install Default Secure Boot Keys. This action loads Microsoft's standard certificate database and transitions the firmware from setup mode to user mode, where Secure Boot enforcement is actually active. After doing this, save and exit and re-verify your Secure Boot state with MSINFO32. For dual boot users who are also dealing with BitLocker encryption on the Windows side, there's an important interaction to be aware of. BitLocker uses Secure Boot as one of its platform integrity checks when it detects changes to the boot environment, including changes to secure boot settings, firmware updates that modify the trusted certificate database, or changes to the UEFI partition. It may trigger a BitLocker recovery prompt, requiring you to enter a 48-digit recovery key before Windows will boot. This is not a sign that something is wrong with BitLocker. It's BitLocker correctly detecting that the boot environment changed and requiring proof that you're authorized to access the encrypted drive. The issue is that many users set up BitLocker without saving or writing down their recovery key, making this a very stressful moment. Before making any secure boot or firmware changes on a machine with BitLocker enabled, go to account.microsoft.com/devices and verify that your BitLocker recovery key is saved to your Microsoft account. If you're using a local account, check whether the key was saved to a USB drive, printed, or backed up to Active Directory if on a domain. Have the recovery key accessible before you make any changes to secure boot or firmware, not after. Let's also cover what happens specifically on virtual machines, because an increasing number of people run Linux in Hyper-V, VMware, or KVM and encounter Secure Boot. Issues in that context. Virtual machine Secure Boot is managed by virtualized firmware rather than physical hardware, which changes some things. In Hyper-V, Secure Boot settings for Linux VMs require selecting a Linux-compatible Secure Boot template. In the VM settings under Security, the Secure Boot template should be set to Microsoft UEFI Certificate Authority for Windows guests or open source shielded VM for Linux guests. Using the wrong template is a common source of Linux VMs failing to boot under Secure Boot in Hyper-V. In VMware, Secure Boot is enabled per VM in the VM settings, and the virtual machine firmware handles certificate management independently of the host. For KVM QEMU, Secure Boot support requires using OVMF as the firmware and correctly configuring the certificate database, which varies by host distribution. In all virtualized environments, firmware updates to the virtual machine firmware are handled separately from the host. So FWEPDM and GR on the host doesn't update the firmware inside the guest VMs. Each VM environment manages its own boot security independently. Finally, here's a quick diagnostic checklist to run through if you're trying to figure out which of these scenarios you're actually in, because the symptoms can overlap, and the right fix depends on correctly identifying the root cause. Start with MSINFO32 on Windows. Check Secure Boot state and BIOS mode. Both should show on and UEFI, respectively. If either is wrong, that's your starting point. On Linux, run mokutel, SB state should say secure boot enabled. If it says disabled, secure boot is off at the firmware level. Run fwupdmgr get updates to check whether a firmware update is available. Run dpkg, L or RPM, QA, and grep for shim to check your current shim version against your distribution's current release. Check whether your EFI partition is intact with ls boot.efis. You should see directories for your Linux distribution and for Windows if you're dual. Booting. If the Linux directory is missing, grub has been overwritten and needs to be reinstalled from a live USB. The pattern across all of these fixes is the same. Identify which specific part of the secure boot chain is broken, address that specific part using the appropriate tool, and verify the fix before closing the session. Secure boot problems feel opaque because they manifest as black screens or firmware. Error messages without obvious explanation, but the underlying causes are well understood and well documented. And every scenario described here has a specific tested resolution path. The 2026 context makes this moment unusual. The certificate transition has created a larger than normal population of affected systems all at once. But it doesn't make the problems fundamentally harder to solve. It just means more people are solving them at the same time, which is exactly why this guide exists.